Thank you very much. I think last time I was here was 4 years ago. It's always a pleasure to be here and also have the advantage, a chance to explain that what we've been doing in the last 4 years. So that's quite nice. I hope you'll find it interesting as well. I'll start with, I will talk about, as Glenn mentioned, let me see, turn this on. There we go. I'll talk about solid-state spin-photon quantum interfaces. So basically, the solid-state versions of what people have been doing for many years on atomic physics. We'd like to use those, thank you for the toolboxes, and implement to physical systems that we think we can control. And if we can't, that's new physics, then we try to find out why. And that's the whole storyline of this field that's been developing. But before I get to the details of it, I'd like to highlight one question. And I think this is as good an audience as any to ask this question. And that is the concept of correlations. So in physics, and you'll see why we're trying to do all these experiments, it boils down to the concept of creating correlations. We'd like to create quantum correlations between things, all right? So when I say things, as a scientist, obviously it's two red blobs is the first thing that comes to mind. I want to correlate two red blobs. And what I find, and please do let me know if there's an answer to this question. But what I find is that you can't get away from the concept of proximity when you're creating correlations. Somehow there is a characteristic length scale involved to describe interactions. And then when you describe the interactions, you may or may not be able to create correlations between say, the internal degrees of freedom of these red blobs, right? So basically, any kind of correlations you're building up in any physical system or any number of particles, there is a characteristic proximity or length scale involved. So proximity as a concept is fundamental to correlations, except one example that I know. So please do let me know if you have other examples. The one example I know that kind of motivates this idea of light-matter coupling is the fact that if I have this red hue around the red blob, that signifies that it radiates, it emits photons, all right? So if these two red blobs can exchange energy directly, then I'm no longer limited by proximity, but how far this light or the photon can travel. All right. So think of it as, let's do an example. Let's put two cavity mirrors here and here. All right. At that point, if I want to create correlations between the two red blobs through light mediating this interaction, then I no longer care about the exact distance between the two objects. What I care about is that the two red blobs sit at good overlap with the mode defined by the light, by that cavity.
It seems there's a third option.
Uh-huh.
You can measure both of them jointly and not have them directly connect to each other, but that joint measurement. Okay.
Thank you. Exactly. Thank you very much. This was pre-planned. No, it was. And indeed, the oddity of quantum physics shows up to give the third option, which is great. And that is, look, they don't even need to interact directly with each other. They don't need to sit anywhere particular, in fact. The only thing we require is that emission, for example, this is one way of doing this, light emission from each of those gets to a third party that does a measurement. It's again, an oddity of quantum physics. You make a measurement to make sure you don't find out what the answer is, but in return, you make sure that no one else does either. And that's the main concept of it. So if you manage to do this, there are protocols where actually you can realize correlations. So this is the universal sign of correlations between these two red blobs, all right? So that's very interesting. Now, purely from a physics perspective, this is nice because it completely removes this element of proximity as a requirement from the system. It opens up the field. From a practical perspective, this lies at the heart of, or let's say one of the key features of building perhaps a feasible quantum network architecture where you don't have to rely on one by one lining up quantum systems with individual access. The overhead of that, you need a third party, perhaps a puppet master, if you will. All this required is that there's line of sight between the puppet master and the individual systems. And they don't need to have line of sight between each other. So that's a quite powerful, let's say, less overhead, suggesting less overhead of control to create pairwise correlations in an ensemble. All right? So that's interesting. And this is obviously what we find quite exciting as well. And it goes back to a 1999 proposal. It's very nice. And the idea is, and this is nice to give this talk here because this was a key place where this was realized with trapped ions. the idea is that you drive both of those red blobs. Now we get to see the inside of the red blobs because we want to talk about what is being correlated. If we have a three-level system, an atomic system, the spin projection can be proportional or dependent on a photon being generated or not. So by having a probabilistic drive on both of those below saturation, you can generate a photon, and if you make sure that you detect the photon but not know where it came from, the idea is this quantum erasure realization, and you end up creating correlations between these two probabilities of which one emitted the photon and therefore flipped its spin. Right? So spin up, down, and down, up are two combinations that are not distinguishable from each other. All right, so this has been realized with trapped ions, and as I said, this is the place to talk about it. In the case of solid-state systems, we want to get to that experiment. We'd like to do those kind of experiments to see if it is possible to treat a solid-state system in this three-level, relatively simple format. And if it is possible, can we actually, how well does it perform? How quickly can we generate entanglement? How good is that quality of entanglement between the systems, and so on and so forth? Over the years, for that kind of a goal, people have been, community has been working quite hard. But these are the three areas I would actually classify the solid-state quantum optics people. You're either a spin physics person, you've been doing a lot of spin physics to figure out how to control and keep it decoupled from a whole bunch of noise sources. Or you're a photon person, you're looking at the quality of the single photons that come out of the system, or maybe entangled photons, and trying to characterize the purity, the cleanness of the optical systems. Or you're actually a cavity QED type person looking into complex geometries, cavities, waveguides, in some cases how to do impedance matching from one system to the next. Each of these require expertise, and over the years, if you look at solid-state-based quantum optics papers, they almost always end with, and therefore we achieved amazing results in this channel, and if we can combine it with the other two, it'd be great, wouldn't it? You paved the way too, and then you point at other people that done this and that. And same thing here. If you've done nice spin physics, you point and say, but it's relatively straightforward to combine the two advancements and proceed forward. And that's actually, finally, we're about in that regime now. We're actually doing those, right? But it's only in the last few years that all of these have matured enough that we can now talk about coupling the expertise in these areas together. All right. There's one more thing I'll add here, local register. That is, at the site of the spin, if you want to define it as a qubit, you do want additional spins or additional qubits to talk to for the next stage of how useful this could be. But I'll leave that as a tag, and I'll refer to it later on in the talk. But for now, we can ignore that. All right, so when I say solid state, what do I mean? Well, I mean much more than this. But at least this is a family of physical systems that spin-photon links have been seen and are being studied actively, some earlier than others, and some are newcomers. Today, the title of the talk is Old Friends and New. This is the old friend, quantum dots, and the new friend is 2D materials. I'll tell you a bit about both. I'll spend more time on quantum dots because I know more about it. About 2D materials, we hardly know anything about it, so it'll be very easy to explain how little we know, but hopefully you'll appreciate that. I won't talk about all these other stuff. The Nitrogen Vacancy Center is actually the Europe's choice of system to pursue quantum networks from the quantum flagship projects. This is a big, massive project right now to realize a quantum network based on atomistic defects in diamond, but it's nitrogen-based. And all I'm going to say about this is look out for the next couple of years. There's a lot of great work coming out for silicon. In fact, all of group 4 color centers in diamond with both spin and optical qualities significantly superior to the NV center. I shouldn't say spin significantly superior, spin matching the quality of the NV center, which is its struggle. So a lot is going to be done. So keep an eye on this field and this particular topic. But I'll start with talking about quantum dots. All right. So what do I mean by quantum dots? These are semiconductors. Indium arsenide is a direct bandgap material. There's work going on here as well on this particular system. It's basically a small island of about 20 nanometers to 3 nanometers, little pancakes, trapped inside a larger bandgap material, gallium arsenide. All right? So it's material-based confinement for excitons or electrons and holes separately. That is our starting point. And then we put them in electrical contact, so we make devices out of them, so we can control some of its properties. We have an n-dope layer, an electron gas, if you will, with a tunnel barrier, and then a Schottky window to be able to apply a voltage in the lab. What this provides is a comfortable region of around 200 millivolts, 300 millivolts, you can easily apply in the lab, of charging plateaus. So we can load up, we can keep the charging state of the quantum dot as empty, like you can see here. The reservoir does not, energetically it's not favored for an electron to hop in, so nothing happens, the quantum dot is empty. This is a great setup to create the energy levels needed for a cascade decay from a bi-exciton to generate entangled photons. But if you just change your voltage a bit, then you're in the regime where one and only one electron is captured in the quantum dot, and then you have a different, completely different energy level scheme, that's something that looks like this, where the ground state, spin up and spin down, are the spin projections of that extra excess electron. The excited state is putting one more exciton into the, or one exciton into the system in addition to the electron, so that is determined by these two, the closest energy levels in the excited state. Right? So it's a 4-level system with selection rules, but these selection rules are also broken to give us a lambda scheme as well. All right? So it's our 4-level system that we work with. Everything I'll talk about today is not going to be on an empty quantum dot, but on a charged quantum dot. So that's our ground state spin, essentially. The ground state manifold represents, if you want, the qubit that we're interested in. This is what it looks like. So remember when I said you're either good at spin or photon or fabricating very nice structures? This is our fabrication. This is a half-ball lens glued on a piece of semiconductor. All right? That's, as soon as you put it on top, you're done. That's your fabrication. But the dots themselves, the quantum dots, are so nice that we typically get around a few million photons per second with very nice optical properties, and I'll show you some of those. All right, so this is a very nice system. You look through this lens, you see these titanium windows, the very thin Schottky window, controlling, and if you zoom in, you see the individual dots, and you sit and play with one of them. All right, that's our experiment. So I promised that it's a 4-level system to work with, so even the photon generation part, keep in mind that we want to do this puppet master kind of experiment that was initially done with ions. We want to generate photons using the 3-level system as the original idea. The idea is you prepare the system into the state, you optically drive it, and then a photon is emitted, having scattered coherently a Raman photon. And you also flip the spin at the same time. So a photon and a spin flip comes jointly. When you do, first thing we need to do is check the purity of the photon generated this way. And for that, usually you do a simple G2 type experiment. You put 2 detectors and check the probability that 2 photons are emitted from this otherwise mesoscopic solid-state system. And it turns out it's relatively clean. And at this point, I think we're more limited by dark counts contributing to this zero time delay than anything else. So we're guessing around 10 to minus 4, 10 to minus 5 regime of excess photon generation, if you will, for this kind of transition. So it's a very clean system to begin with for the purity. All right? These are done at 4 Kelvin. And the wavelength I'm talking about here is around 960 nanometers-ish. The next thing you do is you take that setup, and then you put one more cryostat next to it with an optical path. And that is again, the magical element in quantum optics, the beam splitter. By combining the light emission from both, but deterministic, so you guarantee that one light from each, one photon from each system arrives at the beam splitter. You look at interference of those probabilities. And again, it's an absence of coincidences at time t equals 0 kind of picture. And then when you do this experiment, you're at 93% visibility, fundamental visibility in those systems, the quantum dots that I showed you. Now, it's important to note 2 things. One, there is no cavity to compensate for any spectral wanderings, which is a typical solid state problem. Well, actually, it's a typical any system problem. If your ions are good enough, if there's electrical noise, you will see it, right? That's exactly what we're seeing. Our electrical noise is nearby to our excitons, essentially. Same physics applies, but basically, broadening the transition by cavities helps erase this detrimental effect. In this case, there are no cavities, so even without that, we're at 93% visibility. That's pretty decent level. The second thing that is interesting, which is already a hint that we're going to have some issues with the ground state coherence, is that if I take this, the wave packet of the photon, and we sort of filter out the last 200 picoseconds and remove it, the time filter, then the visibility goes up to 97 already, just by removing 200 picoseconds out of 1 nanosecond, roughly. All right? And then if you do the same thing to the beginning of the photon, it actually goes below 93. So you can tell that what's happening actually is the beginning of the wave packet is clean for both photons, but then it kind of dies off. It kind of, the quality goes away. And this is, usually it's seen if the ground state coherence is not really strong, so long-lasting, and we'll see what that means. The other thing I wanted to highlight here is that we have 2 separate cryostats in the lab, 2 separate samples, 2 separate controls, 2 separate quantum dots. The usual leftover knowledge from many years ago is that, oh, quantum dots are all separate, they're different from each other, so they cannot get them to be the same. It takes us about roughly 1 hour if you have the right samples. It takes us about 1 hour to find 2 matching quantum dots in 2 cryostats. So this electrical control is quite powerful in that sense, and magnetic fine-tuning of the Zeeman splittings for both is also possible. So you can make these really identical as well as can make.
There's another way you could do it. You could use the same quantum dot as delay from, and then that presumably gets rid of the non-identicality of the 2 dots, at least other columns.
That's right. So thank you. When you do that, what happens is should refresh that. That allows you to characterize the noise profile on your indistinguishability as a function of time, the delay time. And what we see is that the beginning is very nice, 98, 99%. And then over some time scale, which is again related to ground state coherence, it actually drops down to around 90, 93%, about 95%, let's say. But if you want to entangle 2 different spins, you are ultimately limited to, obviously, so that system actually, the experiment where you use 2 separate quantum dots is the same as using 1 dot experiment in terms of time scales, doing it at infinity separation, because there's no correlation between the reservoirs that cause delays. All right, so I'm going to flash, as like a sales pitch, flash a few experiments that I've selected randomly. This is obviously not the exhaustive list, but some key experiments and using the quality of the photons quantum dots are able to provide, ignoring everything else, ignoring the spin part of the story. And in fact, this, for example, this one, the multi-photon boson sampling, there's an archive paper now from, again, Chaoyong Lu's group. We need to replace that. This is 10-photon boson sampling. This is quite a competitive field right now. Quantum dots are indeed the only systems where you can generate that kind of large states to do the experiments. Now, that said, we now take off my sales hat. I put on my, let's say, admission to the problems of the system, the proper scientist hat. We want to, that's the photon side of the story, we want to control the spin, right? The spin has to be also good quality if you want to do something with it. Well, let's see what happens. A number of experiments have tried doing good old magnetic coupling of the ground state splitting. There are 2 challenges for this. One is, if your readout is optical, then you need to split this significantly, and that corresponds to many gigahertz. Usually for magnetic fields where your system is clean, we're talking about 10, 20 gigahertz splitting. So applying a 20 gigahertz microwave field is not easy. But in addition, when people did try to do something similar, or at lower fields, the challenge is that they found the ODMR line, the resonance line, magnetic resonance line, but it was kind of, every time it was shifting to another point. It was a bit random. It was distributed, but at each try, it showed up at a different place, which makes it very difficult to say, I'm driving the system on resonance, or I'm driving the system with some detuning. I don't know what I'm driving the system, because it could be anywhere in this much broadened region. So magnetic coupling actually didn't really work for quantum dot systems. So another approach, again borrowed from quantum optics, was employed. The idea is to far detune a laser, pulse laser, strong pulse laser, and actually create effectively this kind of coupling between the 2 spins. This is great. It's a broadband approach. It doesn't depend on how far detuned you are, essentially, in terms of being able to do the rotation. It relates to the intensity of the light. So in 3 picoseconds, you're able to do a Rabi flip, essentially. And this is spin Rabi curves extracted from optical readout once you apply this pulse, right? So we do things optically in the sense you make use of the electric dipole strength of these systems. And then you say, okay, well, what is the ground state coherence? And you do pi over 2, wait a bit, pi over 2, the Ramsey experiment, and you find out that your T2 star, your spin coherence, is crap. There you go. That's 1.5 or 2 nanosecond regime. This is terrible. I mean, now do you understand why we had this issue with the filtering, time filtering of the photon, and we could see the effect because spin coherence, or the ground state coherence, dies off on the order of 2 nanoseconds. The photon itself is 1 nanosecond long. So already, by the time the photon is finished, we've already lost some coherence, and that's that effect, going from 99 to 93, or even lower is due to that. All right. So normally you could say, well, that's not a problem. We can do dynamic decoupling, right? You can enhance, if this is some recoverable noise problem, we should have much longer spin coherence. And if you do spin echo, indeed, it does give us basically a limit of about 10 microseconds for quantum dots. So we have electron spin coherence of about 10 microseconds to work with. It is modest, but it is not nanoseconds anymore. It's useful, and we can still do a lot with this time scale. The problem is this. If I want to store quantum information, some sort of a quantum state in the spin, then I do have that time available because I can do some operations. If I want to generate a photon by flipping spin in a coherent manner, as I was hoping, then I don't have that control of decoupling. I am stuck with this T2 stuff. So the quality of the spin and photon entanglement in the first place, I have to wait for that photon to be generated. That takes about a nanosecond, and I can't do anything to change that. So basically, I'm stuck. So that is a fundamental problem. Even if you can enhance your spin coherence later by decoupling techniques, the initial step is going to get a coefficient that limits the entanglement rate that you can generate this. All right, but nevertheless, let's do the experiment. This is the quantum dot system that we put in. These are the 2 cryos now, exactly the same experiment. And basically, we prepare the spins in the same state. We do this weak probabilistic drive, and it mostly won't emit a photon. Neither of them will emit a photon. Sometimes one of them will emit a photon. That's the subset we're interested in. And sometimes you get 2 photons being emitted, and that's an error, systematic error in our experiments, as usual. And then you choose a basis to make a measurement, and you see if the spins are correlated with the photon that you see in the first round. So it essentially becomes a 3-photon correlation measurement. All right? And this is the result. This for semiconductor quantum dots, we're roughly at that level, 63% entanglement of spins into cryostats. Of course, Z basis is better than X basis. X basis is the most vulnerable one for decoherence, but the average gives us 63%. All right? Now, this is what I think is a reasonable chart distribution of all physical systems and all reported experiments doing exactly that measurement. There are others that have done direct experiments, like Rampe's results and Andreas Worof's results on superconducting systems. I'm excluding those. I'm interested in the third option, where you do a measurement independently on a third party, a measurement-based entanglement. And there are 2 schemes where you can do it in detail. The single photon scheme is the one I talked about, which gives you better rate, but it has a cost of fidelity. If you're able to sacrifice your rate by detecting 1 more photon to correct for systematic errors, then you can increase your fidelity. And you see this distribution, anti-diagonal distribution in that sense. Now, this is entanglement generation rate as a function, or I should say Bell state fidelity as a function of entanglement generation rate. These are all these papers that have done this experiment. Quantum dots sit right there. So that 63% is actually right here. That's the result. All right. So you see what's happening. This rate, the entanglement generation rate, is directly related to the rate at which you can generate a photon, how strong, how bright the source is, and then how quickly can you prepare the system to emit again. Do you need to load? Do you need to cool down? Do you need to do something else? Or is it all ready to go after the first photon being fired? In the case of quantum dots, it is ready to go. That's why it gives us, and it's bright. With only 10% collection efficiency of the photons, it allows us to be all the way up here. But the fidelity is low, and I'll describe a bit about that. One thing we can do with this, of course, is you realize that this whole thing is actually a massive interferometer in the lab. This is a big cryostat. This is another big cryostat. This is actually a table. It's not obviously not a single beam splitter. This is one big table. So these are 2 separate optical tables, 2 cryostats, and a third table that has the detectors. So you're trying to stabilize the lab, essentially. Phase stabilize the lab. And if you don't see entanglement, of course, because your phase, which directly maps into this one, among other things, is going to be completely washed out. So you'll see no correlations if you don't stabilize this phase. If you do, then this error, which is a few degrees in our case, is going to map directly as loss of a reduction of the visibility that we're trying to test. So there's going to be a bit of a loss coming from this technical issue. And of course, if you're able to control this phase, then you can also control where it's going to sit. So you can actually choose what that phase is going to be. And it's a replica, basically, of a previous experiment with ions, where you can actually choose the measurement projects you to a different state. So you can essentially create all 4 Bell states as your starting point for the 2 spin. All right. Yes. In our case, it was intentional because we would actually have to do a lot more building up to make sure that we have 2 independent paths running the experiment. It's just easier. We had the 2 cryostats. It was just so much easier to have 2 fibers coming back to the same setup that we're interested in, the measurement setup, and having 2 separate cryostats to tune each one. Because we also use, as I said, the magnetic field tuning to make sure the Zeeman splittings are identical. So we kind of need local control in this sense. All right, so let's do a mini exercise, all right? If we didn't have that, crap nanoseconds T2 star, but instead infinite spin coherence in the ground state, this experiment would have been technically up here, changing nothing else, all right? So we would have been up there if spin was better than it is. And if the phase stability was actually 100%, let's say, ideal, then we would have been up here. So it would be, quantum dots would be actually quite an attractive system if we had better technical prowess in the lab and also infinite spin coherence. 2 things that you can have. Maybe. And second issue is if we actually use current ongoing techniques, this is my line at the end of the paper, this paves the way to X and Y. If we now take all our results and just add the collection efficiencies due to current cavity QED points, we should be at megahertz, which is nice because that's the rate at which you're generating entanglement faster than losing the entanglement in the course of the step. So this is quite a nice thing to have. So let me talk through some of these. Basically, these are the 3 things. You need to basically improve your collection efficiency. You need to improve the spin quality. And the 3rd thing we need to do actually is remember that plus local register, the extra spins. We need to have extra spins. So if quantum dots are going to be interesting, then you need to have some sort of a spin reservoir that you can control. And we'll come to that later. All right. So the first part, as I said, I won't do it, but this is quite an advanced field by now. We should expect about 10 to 30-fold increase in our photon collection efficiency based on these results. These are from Pascal Saint-Hilary's work. This is brightness versus how good photons are, this indistinguishability measure, if you will. This is where quantum dots tend to lie. Ours was down here somewhere in this window, all right? And I'll highlight this one work, quite a recent work. A lot has been going on in the last few years on having open cavity structures where all these gated systems are present, plus you have a cavity incorporated to it. And Richard Warburton in Basel achieved a cooperative of 150 in his latest work. And the claim is that the 99.7% of the photons are coupling into a mode that they collect upstairs, millions and millions of photons. So this is quite promising that we can actually work with such systems. We don't want to work in strong coupling, but we want to be able to extract the photons, obviously. So instead of our 10%, this is quite attractive to work. All right, I'll talk about number 2. Okay, that's the main thing I can do because I do less photons, more spins. And the source of this error, and my promise now is to give you infinite spin coherence, all right? That's what I'll promise. So the idea is that you have this quantum dot actually has around 50,000 nuclear spins. Right? Each one of these has a spin. Indium, gallium, and arsenic all have spins and also isotopes. So it's actually quite a noisy place for the electron to be in. The electron wave function is as big as 50,000 of these guys. So electron is in contact, not even dipolar interaction, contact interaction with 50,000 slowly wandering nuclear spins, which are at thermal equilibrium at 4 Kelvin. So we're not even cooling them, right? So that's a problem. And the fact that this is contact interaction means that this hyperfine interaction is very strong, actually, not weak background noise, but quite a strong coupling. And these fluctuations are seen by the electron as Overhauser field, and the electron spin itself is seen as night field. These were interesting physics problems that were solved, say, about a decade ago with quantum dots, to understand what's happening. Now, I don't care, in this work so far, I don't care about the interesting physics of nuclear spins. I just want them out of there. I don't want them, right? So unless I go to silicon germanium type systems where there is no nuclear spins, the only thing I can do trying to salvage here is to reduce their fluctuations. Okay, one way to do that is to polarize them. So if we polarize all the nuclear spins, fluctuations will go away. It's the fluctuations, time-dependent fluctuations, slow wanderings that cause the problem. Good. And people did that. So they can do it by dynamic nuclear spin polarization. They can optically drive the electron, which leads to, due to this coupling, polarizing nuclear spins. And they achieve 70% nuclear spin polarization, which is amazing, right? You have this 50,000 nuclear spins ensemble with 70% polarization. It turns out it's also useless because fluctuations due to 70,000, due to 70% polarization is roughly the same as none. Only when you get to 95% or so, fluctuations are reduced significantly that you actually see the effect. So it's great, but useless. And in turn, if you do this polarization, you end up with something like 5 to 7 Tesla extra magnetic field due to this Overhauser field. So the electron is split as if you're operating a 7 Tesla magnetic field, which you certainly don't need. It makes the coupling even harder. So it actually is the worst idea. But there's an option B, and that's what I want to talk about today. All right, so to understand where I'm going to go with this, my main goal is not to polarize them, but to quiet them down. All right, think of it as a Zamboni. I want a Zamboni machine to quiet down the fluctuations on the nuclear spins. So the idea is, until now, spin control, coherent control, was done optically, yes, but it was done with a broadband field. Right? It was an ultra short pulse, and it didn't actually rely on particular Zeeman splittings of these guys. Any Zeeman splitting would give us the same kind of rotation for the electron spin. We wanted to change that because we want to have access to this internal structure. So if I represent spin up and spin down, instead of saying just blurry lines, I actually should write it in this format, that you have the electron spin down manifold and electron spin up manifold, determined, including multiple lines, each corresponding to a single nuclear spin out of this 50,000 or so. All right? That's what the actual levels should look like. And of course, at thermal equilibrium, these are occupied. Hundreds of these levels are occupied because nuclear spins are spread over in a mixed state. All right? So what we've done is we use the same concept, but with narrowband lasers, and we mix microwaves with narrowband lasers, effectively giving us direct coupling to this transition. So we can actually probe where that spin resonance is. All right? But still using it optically, so it actually works fast. So if I take that energy level and rotate it, our system now looks like this. The electron nuclear system looks like this. So this is the electron up manifold. This is the electron down manifold again. And each of these is one nuclear spin flip. The Zeeman energy seen by the electron due to one nuclear spin flip.
But you're showing the proportion of the thousand.
Absolutely, absolutely. This extends that way, this extends that way. There should be about 50,000 of these. And it's the state, when I say where is my state, it actually is spread over a few hundred of these. Now, on top of this, what I call here, is omega, is the 2-photon detuning that we select that is resonant with one particular net nuclear spin polarization, whatever it might be, let's say 0, all right? That means this is, in this picture, if I go back, here, this is that splitting, and I'm resonant with a particular IZ, all right? But that means that one nuclear spin flip, I'm no longer resonant. Now, this is slightly different than harmonic systems because IZ is the field that the electron will feel due to nuclear spins, essentially. There's a magnetic field called Overhauser field. So if I change IZ, the net field the electron sees, and therefore adjust the Zeeman splitting is based on that. So I actually, this is actually an unharmonic system in the sense that each IZ will have a corresponding splitting for the electron that we can target. So in a way, this does not drive all of them. So I cannot do a nuclear spin not flipping, direct electron spin flipping transition regardless of IZ. I can only do for a given IZ. All right? Are you with me on this? This is key because that gives us the unharmonicity that we'll be using later. But due to the quadrupolar coupling that's present in these quantum dots in the presence of strain, so these are not isolated quantum dots, they're under strong strain. Strain allows that transition to be available. Normally it wouldn't be, but it allows that to be possible. Because this is possible, now by actually driving this, you're also driving a bit of that. So that is also allowed. Okay, so you can flip a nuclear spin that way. However, this is also allowed because you're also populating the system, but this is stronger because it is closer to resonance than the other one. The unharmonicity kicks in here, and the surprising thing is if you do it on the other side, you see that they're both pushing the nuclear systems towards where your laser is. IZ, in this case, is purely determined by you. You set your two-photon detuning in the lab for the laser, and then let the system, just drive the system for a while. As you do this, more and more of these guys getting pushed this way, and more of these guys getting pushed that way. So you're, in a way, you see that you're sweeping the thermal distribution that you had to a narrower distribution by optically driving, all right?
Okay, so this is optical pumping into a specific chosen value,
But not at the extremes.
I'm sorry?
But not at the extremes of the, so
Right,
we're not
so
doing,
you work near the center where most of the
that's right.
of the population is, but presumably to have a big effect, you'd want it to draw in tens or hundreds of such
Absolutely.
states, and this does it. That is,
Yes.
this thing that you've shown as being nearby actually
Extends out, that's right.
tens of-
Exactly. The key point is the ratio of the two arrows, the two directions. If you are able to sustain the fact that this is stronger than this rate, when you go far out there as well, that's actually crucial. You still need to sustain that so that you can bring all those outliers in as well. Otherwise, you end up reducing a narrow band, and then the rest stays the same. You're absolutely right. So it does seem like it is actually drawing in significant portion of these. And I'll show you the results. So essentially, there's a feedback mechanism to the thermal equilibrium. You end up with a non-thermal distribution. That's right. So that ratio, the difference between the two directions is getting less and less and less, and it vanishes at some point. So you have finite range over which you can match. I can spoil it. Basically, our simulations suggest that we're cooling 35,000 as opposed to 50,000 roughly that we expect for nuclear spin. So that's, but it's still a good portion of it.
Well, if your time scales were right, you could always sweep. That is, you could.
And that works as well.
But how good are your time scales? I mean, you're fighting against the fact that the thermal.
It's also trying to. Exactly. So that's coming next. So let me keep going.
Collaborate. Collude, I guess, is the right word.
You didn't realize that we organized this talk together, actually. But anyway, so the key point I want to highlight in this kind of drive is the spectral selectivity. That's what we're going to rely on. So it's essentially, I'm going to present optical electron spin resonance. That's the power of this technique that allows us to probe in here what actually happens in these levels, and can we probe. So when we do this experiment, so essentially the idea is if we are genuinely cooling the nuclei into a lower state, then smaller distribution, then this is kind of what it's going to look like. The spread is less. And indeed, we see this. So this is the ESR, optical ESR experiment, the two-photon detuning that is swept over time with very low power. So that we're trying not to disturb the system. We're only probing what the distribution looks like. And indeed, this is what electron spin resonance is when you do a poor job at preparing, and when you do it well, then it looks much narrower. So this is exactly along the lines that we were thinking before. And now what it means is that this line width suggests now 15 megahertz as a figure of merit, and I will not say that this is the temperature of the system because not at thermal equilibrium, so I can't really quote a temperature, but if I were to quote a temperature, it would correspond to a width that's on the order of 500 microkelvin, right? So, but I won't quote that temperature.
But you're saying it's not even spin temperature. You could separate out the spin temperature from other temperatures, but you're saying it's not really a temperature because it's not, the distribution doesn't look like that.
Exactly. It's not thermalized into this temperature, and then I can quote it. But if I were to take the width of the distribution that we're saying, without looking at the actual physical functional form of it, then it looks like it would correspond to as if we had cooled and thermalized at 500 microkelvin, just to get an idea of the fluctuations at the end. All right, so then the whole point was to give you infinite spin coherence. So let's do that. This is Ramsey. And of course, we get the low few nanosecond spin coherence. That is the problem. Now, if I include this preparation stage that I talked about to quiet down the nuclear spins, and then as soon as I do that, we probe to see what T2 star we're able to get for the electron, and that becomes around 40 nanoseconds. So the electron is now living without any protection, is living in this quieted spin system that is non-thermal. That's the Zamboni I'm talking about. You do the Zamboni, and then the ice is nice and smooth for a while. Now, given that I'm only interested in T2 star because of the photon generation, and given that it takes about a nanosecond to generate the photon, infinity and 39 nanoseconds are the same. their effects are the same. So there you go. I promise you infinite. That's it. Infinite means 39 nanoseconds in our system. It's reasonably well. There's no point increasing this more, basically. We won't win for the quality of the spin-photon interface. That's already enough. But then comes this question. So this funny non-thermal distribution, how long does it last? How long can I preserve this T2 star that I was talking about? It turns out it's actually quite reasonably long. It's about 50 milliseconds before T2 star drops back to its original value, or the 1 over E value is 50 milliseconds. So this funny nuclear spin profile actually lives quite a long time. So indeed, I can prepare nuclear spins, and then if I can address other parts of it, it's perhaps possible. 50 milliseconds is quite long for us. And then, but there's one other feature. So if I look at this, I did tell you that this width is 15 megahertz, but it's single nuclear Zeeman flip. This difference is 25 megahertz. So actually, we didn't just quiet down a bit. We are in the regime where we should be able to resolve this transition and that transition, the first sideband and the second sideband. This is the sideband resolved regime in atomic physics, essentially. So we should be able to see the sidebands that we weren't anticipating initially. So then what we do is we coherently drive the system, and then we drive and then sweep the ESR line to see what lit up, which states lit up. And indeed, we do start seeing some features coming up. And if I do a line cut, then this is what the uncooled system looks like, and this is what the cooled system, when we drive it for a while, looks like. So you're able to see the original ESR line. You see the first one. This is one nuclear spin flip out of 50,000, two nuclear spin flips, and whatnot. All right? Now, normally, there's a difference between just driving the electron or driving the electron and the nuclear spin flip at the same time as a second-order process. Normally, these guys should be all the way down here. If I am flipping one nuclear spin, right? It's a second-order process. It's very unlikely, so it should be down here somewhere. There should be tiny little ripples. But the difference is, I'm not actually exciting one, as in one person in the stadium is not going and waving. What we have actually is a spin wave. So the whole stadium takes part collectively. So we start one wave going around the stadium. That's this one. A second wave going around the stadium, independent from the other one. And that's this one. So it's a collectively enhanced process. That's why we don't see there's a tiny blip down here. Even though it's second order, we actually see it much stronger. And if we check that, the factor that we expect to see is indeed matches with the root of 35,000 essentially contribute. All right. So what it means is that we're able to start these spin waves inside a little quantum dot. The whole point about quantum dot work for many years was to make it more and more and more as simple as you can imagine. The 4 levels or the 2 levels, whatever you wanted to do, isolate from everything else. But the more we managed to zoom in, we managed to open up to all of a sudden coherent access to 50,000 or 25,000 or 35,000 nuclear spins, essentially. So what we want to do next is drive this transition, prepare the system into this fused state distribution. We're not able to do it only on single one yet, so it's still distributed a bit. But once we get there, we want to coherently drive one of the sidebands and see if we see some coherent exchange between the electron and the nuclear, Zeeman levels, if you want the nuclear magnon in this case. And so we chose this one to be far from these guys because we were simultaneously driving everything, actually. We're not doing it very cleverly. But when we do that, we do indeed see signs of coherent oscillations, the first signatures of exchange going on between the ensemble and the single electron back and forth.
So why is the noise, when you're doing these sideband resolve transitions, so small, and the noise is so big when you're doing it? Is it just because the lack of cooling produces all those fluctuations?
You're talking about the difference between...
on the red curve are huge compared to the fluctuations.
Yes. It's interesting, actually. It's partly time, it's data acquisition time, so part of it is technical. This is more a reference point, reference measurement rather than the same quality to be able to resolve this, partly. The other part is you're actually driving. So there's, even though we're operating at low power to make sure that we're only probing the system, we're not only probing the system, we're still cooling. So it's the same mechanism. So we have to do this quickly to avoid actually deforming the profile. But otherwise, there's no reason for them to be separate. I think their effect is probably the same. The number of atoms that take part in creating this width is the same. The number of atoms contributing to this is probably less, but not much more than not more than factor 2. All right, so the latest from the lab now is when we look closely into this, remember, this is a composite system, right? These are not 35,000 nuclear spin 1/2 particles. We have indium with 9/2. We have gallium and arsenic with 3/2, and their isotopes as well. So it's a pretty messy system. So first of all, it's amazing that we can actually resolve it in the first place. It should be all blurred out. But if we zoom in and do a bit of careful measurement, then we're starting to see now more systematic. This is really hot from the oven, so I'm not going to say too much about it until we're confident, but it looks like we can repeat these measurements many times and identify these two particular species. So we can look in to the subset of species in this alloy-looking ensemble. It looks like from their split. All right, so basically the directions we'd like to go with this is twofold. One is the advantage of having this nearby deterministic spin, so not deterministic, probabilistic spin, where you do dipolar coupling, is that it's there, as long as you find it, for say in V centers, there are a few nuclear spins around, you find where they are, and they become your resource. In the case of, say, rare earth or ensemble quantum memories, you have to convert your information from your spin to a photon, and photon gets absorbed into spin waves. It's a very similar concept as what we have here directly, but then there's this photon loss and photon absorption rate coefficients coming in. This gives us a chance, if we can manage to get the quality to be reasonable, it gives us a chance to actually combine the nice sides of both. The collectiveness of an ensemble absorbing or storing the information with the nature of control to each one and deterministic aspect of it without an interface, direct coupling without an interface. And of course, you can do a whole bunch of other stuff, but we need to get to that. This is more a motivation for us than the next steps that we're doing right now. I'll pass this. There are many questions that we need to answer. I'll pass this for now for the limited time. What I'll do is for the next, something like less than 10 minutes, right? 5 minutes, something like that. I'm going to switch completely now. All that is fine. I'm going to switch to a topic I don't know. As I promised, it's not going to take long, but it's entertaining. It's these 2D materials, all right? And they're, Glenn can correct me, but I think with 3.5, for example, you work very hard to produce very good quality samples, heterostructures and all of that, and then you go home, and then you dream of this. You dream of being able to make atomic layer precision of any arbitrary material on top of the next one, if you want to, for any reason, of any property from this chart, this table that you have. You can have a superconducting layer, plus an insulating layer, plus a semiconductor layer, plus a semi-metal, a magnetic one, and a non-magnetic one. Any combination you want to create both actual working heterostructures for a particular purpose or emergent new structures, new features through the alloying that comes from this kind of control. So there's a lot to swallow in this whole business. There's so many opportunities, but also there are a lot of technical challenges in material quality and all of these. But nevertheless, it's a very hot topic. And there's this one issue of nature nanotechnology that basically had 4 papers back to back talking about confined emission from these layer materials, these transition metal dichalcogenides. So this is monolayer, basically. It's a 3-atom atom complex of WSE2, tungsten diselenide, for example. And these 4 papers, plus Rudy's paper in Optica, all 5 papers essentially, all reported more or less the same thing, saying there are local spots that emit light that shows anti-bunching. So these are some confinement centers, and no one knows what they are. Except, I mean, you can see in the title that they're a bit suffering to label what it is. So it's a bit vague. And we didn't do this first, but I was Attache's postdoc, Nick was my postdoc, Chao Yang was my PhD student. I had nothing to do with Marek, but the paper is great. So we said, okay, we'll look into it too, because it's an interesting material, and there's a lot of new physics in there to study. So the way it worked was we had a student who was very good at fabrication and just could not see these quantum dots, these localized emissions. And we had another student who was, let's say, efficient with time, in and out of the fabrication lab, very quickly producing samples, and miraculously having many of these emitters. So the two people doing more or less the same recipe, the recipe is borrowed. We are foreign to the whole field, so we borrowed the recipe and we executed it. So two people made very different, end up with very different results. Turns out, the person that went in and out very quickly was a bit sloppy in terms of removing all the fabrication errors and leftover junk, essentially. All right. And then when we looked at the AFM, we could actually see these bumps, tiny little bumps left over under the otherwise flat material. So we said, why don't we make it so that the other student does the fabrication from now on, so it's clean, but we introduce the bumps ourselves deterministically. So this is in collaboration with Marco in Harvard, Marco Lonchar. Basically, this is silicon nanopillars. We etched out nanopillars, and then you put the material on top. Instead of trying to make it flat, you actually create like TP tents, periodic TP tents. So the idea is if local bending or strain is the cause of confinement potential emerging that captures excitons, then we should see the top of these pillars light up as quantum sources if it works. Right? That was more gut feeling. And this is what it looks like. This is one nanopillar. This is the material on top spreading, and we're looking for features here. What you see is that it's actually stretched down to the base to hold on. So it's actually a stretched material, essentially. All right? And this is a monolayer and a bilayer of this material in dark field microscopy, so you see where these peaks are. And then if you look at the top of these pillars, you actually see quantum emission, narrow lines on each one that show anti-bunching. Indeed, each one of these pillars does generate a quantum emitter. I still don't know what it is, but basically it suggests that it's not defect-based, but rather confinement-based due to local strain in this case. And what is nice is that basically we have about 96, 97% yield. This is even better now. So every pillar more or less has a quantum emitter. So I can guarantee you a quantum emitter to be present. And in fact, half of those will have only one emitter attached to it. And pillar height reduces the spectral bonding. So these are, looking for the first time, actually better than naturally found ones. So this is like a nice advantage of these systems. And it's independent of materials as well. This is WS2 that also does the same thing. In these experiments, this is like 4 or 5 microns, just to make sure they're much closer, so you have a modulating potential to do other interesting things than quantum emitters. There's one paper, if you're interested in, that talks about how confinement potential can arise over a small spatial, let's say 20, 30 nanometers by band mixing. I won't go into that, but I'll highlight two experiments very quickly. One is you can functionalize the pillar itself. It doesn't have to be just silicon oxide. If you put diamond, you can actually talk about perhaps coupling spins to each other. Or you can talk about not one layer, but multi-layers, and then you can talk about indirect excitons. Right? And that's the one I'll very briefly show the latest results, because we're excited about it. I'll pass these. Oh, this is with a nanodiamond, by the way. This is to show that if you just put, we don't even make pillars, you just sprinkle some nanodiamonds on the surface and put your layered materials on top of every nanodiamond, you get a quantum emitter that just shows up. It's all self-aligned. The gallium nitride, same thing. I'll highlight this work from Stefan Strauff. And this is, if there's anyone here who had to work with plasmonics and had to put a quantum emitter in the hot spot of a plasmonic structure, your paper most likely ended up with saying, we observed this much coupling. It could have been that, but positioning the emitter at the 2 nanometer window is very difficult, and therefore we didn't get it. So it probably ended up like that. This is one example where this goes away. Stefan actually decided to put gold nanocubes onto layered materials, otherwise flat. There's no emitter or anything. But as soon as you put gold, it actually creates tension, or stress, I should say, at the 4 corners. And then it actually produces quantum light emission from there. They become the confining potentials. This is irreversible. If you remove, of course, the cube, it goes away. So I don't know any other quantum emitter that depends on you. You push a button, your finger, essentially. You create a localization, you get quantum light out. If you move your finger, it will follow you. It's aligned. If you remove your finger, it goes away. So I don't know any other example of this. But anyways, he's able to see 46 million photons per second from this layered material as anti-bunched. This is quite impressive result. Anyways, what I'll show is one final thing, and that is what we want in these systems is actually long-lived excitons. These are typically living on the order of a nanosecond. Actually, this is quite relevant to dipolar gas work as well. can we actually have excitons in layered materials or in any solid state system that actually has much longer interaction than the simple single particle picture? And the idea for solid state systems in realizing this, let's say, polar molecule concept is to create the exciton not in the same spatially confined location, but separate the electron and the hole. So the simplest thing you can do with a multi-layer system. So the hole sits here, electron sits there, for example. And if you look at the band, valence and conduction bands of these layered materials, we pick WS2 and WSE2, and I'm looking at that transition from here to here as the lowest energy system possible, all right, as the transition. So I'm looking at that system where the electron sits in one material, WS2, hole sits in WSE2, and there's a permanent dipole built in place. Permanent dipole means it will have a very long lifetime, and now we can talk about how these dipoles will interact with each other. So this is our structure, two of those overlapping together. The bottom line is this picture. We're seeing lifetime. This didn't show because of Mac, so the mystery is there. This is microseconds. What we're able to see is actually, it's unfortunate that you're not able to see, but it's a few microseconds of lifetime for the excitons. This is the longest we've ever seen in these materials of excitons, dipolar excitons living for a long time. This is on pillars again, so every pillar has these excitons, and they're confined, they're long-lived. But what's interesting is that if you go away from the pillars, even just the substrate flat region, you're getting dipolar gas, essentially. We can see that they're interacting in a repulsive way to each other, and with a lifetimes of a few microseconds. So it gives us a whole new range of time scale to probe in terms of interacting excitons with each other, in the absence of any polariton picture or cavities in there. All right, I'll pass this. This is being able to gate the quantum dots in these systems as well. And I'll just finish off by saying thank you very much for your attention, and please do join us if you're interested in our